As we have been discussing, the x-axis contains all the information that is required of the geometry of the diffraction, and the y-axis contains all the information about the structural aspects. We see a typical pattern, XRD pattern, which is shown here, where we have marked the possible peak positions associated with these, and the dashed lines here are the ones which are calculated structure factors. We will see how calculated intensities, we will see how it comes up. And then the one below here shows the difference between the observed and the calculated, essentially helping us to determine the structure of this material by the so called Rietveld refinement. So, in the next maybe half an hour or 1 hour, we will try to cover all aspects related to this powder diffraction techniques, because this is something which is quite relevant in industry, and also it is quite relevant in teaching modules. And at the same time, of course, we do not forget about the symmetry that we have and we can associate with powder diffraction patterns. So, the questions which we can answer, in fact, by just a record of I versus 2 theta on a powder sample. We discussed yesterday the 3 modes of data collection. So, let us say that this is a typical standard X-ray data which is coming from the reflection mode. So, we take this pattern, and what are the contents of this pattern? The contents of this pattern are, it contains information about the structure. It also tells us about the crystallinity. If you look at the background associated with this recorded pattern, you see the background is slightly falling, but essentially remaining more or less a constant. The more the constant it is as we go to higher angles, it suggests that we have a very crystalline material, because the peaks are quite sharp and the width of the peaks are not so very different from each other. They are normally about the same size. In fact, the techniques of analyzing the peak widths and so on also gives us several other information associated with it, apart from crystallinity. The other aspect is, once we have a compound like this, we can also question and answer the phase purity questions. A pure sample will have a unique powder diffraction pattern. So, powder diffraction pattern is almost the fingerprint of a given material. So, that way the presence of the databases, the inorganic crystal structure database, the Cambridge structure database, it has all the data sets associated with single crystalline structures. On the other hand, ICDD database, the International Center for Diffraction Data, has information on all the powder diffraction data which has been collected over the years. So, very closely related compounds will resemble each other as far as powder diffraction is concerned. If you have just done for example, some changes in the alloying conditions, or some changes in materials, or if you have made some changes by substitutions, by changing one atom to the other and so on, the powder diffraction pattern will not be very different, but it will be different from each other, as I said, because it is the fingerprint of the given material. So, phase purity is one possibility which we can analyze. More than one phase also can be analyzed in a powder diffraction analysis. We will see as we go later. And we can also determine the size of the crystallite by measuring the full width at half maximum. There is what is known as a Scharer formula which will give us that information. We of course have to worry about the instrument characteristics. We discussed already the modes of data collection in the previous class, but apart from that, depending on the instrument, the width and the so called asymmetry associated with the peak, because the peaks may not be exactly symmetric, as we see in this example I have given here. It may become asymmetric, and that probably is due to the way in which we collect the data. So, the instrument characteristics also play a very crucial role. The peak positions and the intensities, of course, we already said that peak positions has the geometry, the intensity has the structure. So, when we come to pharmaceuticals particularly, the questions come about the active pharmaceutical ingredient. Once they make this compound ready, they would like to ask what is the characteristics of this API, whether this particular API is identical to the API which has been marketed by someone else, or this particular API has the issue of what we call as polymorphism, which means that it may have a different crystal structure. So, questions on polymorphs, co-crystallization, which would mean the formation of co-crystals, the formation of salts, the formation of eutectics, those kind of phases will also come into the picture. We can also work out in the case of tablets, we can analyze the tablets directly, other required materials for tablets apart from excipients and the API, and then we can also analyze the capsules and aerosols. So, these are some of the advantages with powder diffraction which probably we will not have with single crystal diffraction. Other than that, of course, all the information that is contained in a single crystal diffraction is available in this one dimensional profile of the powder. So, in some way or the other, this one dimension profile has to be broken down into 3-dimensional reciprocal lattice information. Once we do that, we can determine the structures even by using the single crystal approach. So, this is the basis of it. So, we will now go systematically through how we index a given pattern. LAB6 is the standard compound which is supplied by many of the companies. They give us routinely this compound, and it uses copper K alpha radiation. This is the diagram we will get, this is the diffractogram we will get. Always call this as the diffractogram or X-ray pattern. Do not ever call this as X-ray spectra, because X-ray spectra means something else. Anything to do with spectrum or a spectra means something very different, because what it means is that you have a ground state of the material and it is taken to a higher excited state, and then there is a radiation which is emitted from the excited state to go back to the ground state, because it can't stay in the excited state forever. There is a time lag in that particular period in which it comes down to the original ground state, and when that happens, whatever comes out as radiation is the spectra which contributes to the spectroscopy. So, all spectroscopies therefore have a time component associated with them, and therefore, we can straight away do Fourier transformations in spectra, because the time component is built in there. In diffraction, we cannot do the straightforward Fourier transform unless we solve the phase problem. The phase problem is overcome in case of spectra. So, the important point to remember here is that this is not spectra, it is essentially the scattering that occurs. We have discussed enough of the scattering over the days. So, it is not spectroscopy which is involved. So, what we should therefore always say as a diffraction pattern or a diffractogram, and X-ray spectra is reserved for some other phenomena which can also be done. One can do X-ray spectroscopy, different kinds of X-ray spectroscopies using electron beams and so on. So, depending upon the crystal system, we have already seen this table some time ago. The value of D of HKL can be calculated depending upon the nature of the crystalline material, that is whether it is a orthorhombic crystal or a hexagonal, tetragonal, cubic. Of course, monoclinic and triclinic will have more complex expressions. So, in the case of a cubic system, it is a fairly straightforward calculation. So, suppose let us say the given diffractogram belongs to the cubic system. We will go through a very quick process of how we go ahead and index that cubic picture. So, D of HKL is A, which is the cell dimension, divided by h square plus k square plus L square to the power of half. Now, this quantity h square plus k square plus L square, we can write it as S, and that has to be always an integer, because h, k all are integers. So, the h square plus k square plus L square should also be an integer. So, it can take values 1, 2, 3, 4, etc. So, let us take a situation where we use this. Let us take this example which is given here. This is the intensity versus 2 theta. So, we take this example to show how the indexing process is done. So, what we do is we have of course 2d sin theta lambda, from which we can write d HKL in this particular form, where S is the value of h square plus k square plus L square. We say S can take the various values. The values of S can be 1, 2, 3, 4, 5, 6 as it is written here, and then we assign the possible HKL planes in a cubic system. Remember, in a cubic system, A equals B equals C, alpha beta gamma are 90 degrees. So, whether it is 1 0 0 or 0 1 0 or 0 0 1, it is the same. So, this is the associated multiplicity because of the symmetry. So, again you see symmetry is the dominant factor in any diffraction experiment, even in the case of powder diffraction. So, when S is equal to 1, the only value we can assign to HKL is 1 0 0. So, when it is 2, the only value we can assign is 110, because h square plus k square plus l square has to be s, and that has to be an integer. So, 3, 4, 5, 6 therefore has well defined HKL values. So, we can therefore assign HKL values to the peaks which we find in the diffractogram. So, the values of the HKLs can easily be identified in a cubic system by just giving the value of S and giving each and every peak the corresponding value of S. S is 1, 2, 3, 4, 5, 6, and you see that there is no way we can assign 7, because h square plus k square plus l square, if we take 3 integers, it will not add up to 7. So, 7 is forbidden. So, as a consequence, we now have uniquely indexable pattern, and so we get these HKL values. Once we have these HKL values, we can calculate D of HKL, and once we have D of HKL, we can get to the A of HKL, because D of HKL can also come from say D is equal to lambda by 2 sin theta. So, we can get the D HKL value, which is lambda by 2 sin theta, from the 2 theta value here. We calculate the sin theta value, and lambda by 2 sin theta will be the D of HKL, and this is equal to A divided by h square plus k square plus l square. We have the HKL assigned here, and therefore, we can get to the value of A, which is what we want, because we want to find out the cell dimensions of the given crystal. So, this is the easiest example with which we can illustrate, but normally there are lots of programs which are available in open websites, and these are all automatic programs for indexing. The logic in which it goes is that any given pattern is considered to start with is a cubic system. One of the requirements that it should have is that it has to satisfy these conditions of the integers being there associated with it. So, if we cannot assign the peaks which come in the diffractogram to these values of S, then we know it is not a cubic system. So, slowly we go up in the reduction of symmetry. So, we reduce the symmetry to tetragonal, hexagonal, trigonal, orthorhombic, monoclinic, and triclinic. In that process, we get evaluation of how well the pattern is fitting the assigned HKL values, and as a consequence we get to the cell dimensions, and then we look at the possibility of identifying a unique cell dimension that can be indexed. So, this process is known as indexing, and this is now very automatically done in many programs, and the standard programs that are generally used are the triar, which essentially means trial and error. What is it? Trial and error method. Trial and error method, and we also have the the program called Dequal. We have several other programs. There is a package called CrisFire which is available, but apparently of late the CrisFire has some problems. So, you have to be careful when you download CrisFire, because CrisFire used to work on earlier operating systems. The current day improvements in technology in computer science, and also the incorporation of now the modern day memory boards will not allow CrisFire, the old one, to run, but then there are other programs. The best package that can be used for every purpose, starting from indexing the powder diffraction to structure solution, is the YANA, and this package is again downloadable free, and this can be accessed through the web. So, these are the programs which will automatically index a given pattern. So, whatever be the crystal system, in principle, following this methodology roughly which we mentioned, we can determine the unit cell dimensions. Having determined the unit cell dimensions, what are the questions we come across in X-ray? We already discussed what is the content of the XRD pattern, in a powder XRD pattern. So, I thought I will sort of highlight the uses that are relevant in pharmaceutical industry, and also in general it should be chemistry. So, one is the phase composition of a sample. This is very critical, particularly if you want to generate a new pharmaceutical material. So, we therefore do a quantitative phase analysis, which is possible to determine the relative amounts of phases in the mixture. So, suppose we have a mixture of phase 1 and phase 2, both of them will be inside this particular diffractogram. And as I mentioned that each and every material is like having a fingerprint associated, and that is the powder diffraction pattern. So, if you have two different compounds mixed into a system, the two different compounds will give two different types of XRD patterns. By type I mean even the full width at half maximum will be different, the shape of the peak will be different, and so on. So, effectively the profile of the peak which comes in a diffraction experiment is characteristic of the material, and therefore, if we do the analysis of the profile, in principle we should be able to find out the possibility of more than one phase being present in a sample. So, the way in which we go about is we determine the unit cell parameters and of course, Bravais lattice symmetry, index peak positions, then lattice parameters can vary as a function of and therefore give you information about alloying, doping, solid solution, strains, etc. These are all very critical in pharma industry. The other most important aspect is, since we say the profile is characteristic of the material and its profile fitting is a issue which we can sort out in order to get all these issues completely analyzed. One can also determine the crystal structure by what is known as a Rietveld refinement, about which we will spend a few minutes as we go along. And this is the refinement of the entire diffraction pattern. See whether we when we make an analysis and identify a phase and then we want to doubly verify that it is a single phase, the best approach is to always use the whole pattern, the complete pattern, rather than use patches of this reflection, that reflection, and so on. Remember, when we did the indexing, we read out the peak positions. We did not bother so much about the way in which the peak is appearing, the shape of the profile, and so on. But it is important that we use the shape of the profile, because the shape of the profile is definitely represents the integrated intensities. So, it is the integrated intensity we will need in order to calculate, in order to determine the structure, because we already know that structure is along the y axis of the powder diffractogram, and therefore, we have to analyze these profiles extremely carefully after indexing those patterns. It is not necessary that we have to index only some 10 or 12 reflections. We have to, in fact, in principle indeed index the entire diffraction pattern. Some of the peaks may be weak, some of them may be strong, and we have to identify all possible peaks which appear once we have the crystal system which has been analyzed. So, these are some of the issues which are essential for pharma industries, and this is where careful analysis has to be done, particularly when we are looking at the identification of possible new polymorphs or comparison of synthetic protocols, lesser efforts. Maybe you have a 2-step procedure to make a API, somebody else has a 10-step procedure to make an API, but have we really made that API? So, such questions come up, and the better, of course, the other issue is better particle size for better solubility. Solubility is a major issue in case of pharmaceutical materials, particularly most of the pharmaceutical materials are delivered or administered in solid form, and therefore, the powder diffraction of these materials becomes very, very crucial. So, this is a very basic technique that has to be employed in pharma industry in order to characterize these solid pharmaceutical materials. So, what are the access points which we have got to do this kind of an analysis? Of course, we can always record a powder XRD of a given material. It is a very easy procedure now. It is not like we spend a lot of time to grow a single crystal and get the single crystal diffraction data. Powder is already formed in our experimental protocol. But is this powder a pure powder? Is this powder a crystalline powder? How crystalline is the powder? How much of non-crystallinity is associated with this powder, or is the powder amorphous? These are all questions which come up. And when we want to answer those questions, there are certain plus points which are available already. So, first thing is we have to check, if we want to determine the structure, check if the structure is already solved. So, there are several websites which are going to help you out. One is the Inorganic Crystal Structure Database, ICSD, the web address of which I have given. And in fact, 4% of this is available for free online as a demo. So, one can use that and get an inkling of how to use the ICSD, and then it can be put on order. Crystallography Open Database, which is available in this website, where you can get some information, if not all, about the structure. MinCrystal, which is having this website information, we can also go there and get to the data. American Mineralogist is another source where we have all the data on minerals which have been and in fact the classification is also available among the minerals if one goes to that site. The web mineral again is another subset of American mineralogist kind of a thing, and there again we can get information on the minerals. Other than that, we have the databases. As I already mentioned, the International Center for Diffraction Data is the one and the most foremost available ICDD package, which will be using a program, a package called PDF4, which can be bought at a cost. And then of course we have the Linus Pauling file for ASM International. It's actually a subsection of ICDD. The best is to of course access ICDD, because that is the one which has all the possible data collected so far on the surface of the earth. In fact, they have some data sets collected in space as well on some powder data. So they have everything in store, and it is easy to access the ICDD database. And of course, if you want the single crystal data, and then ICDD is also linked to the CSD now. So you can link these two, get all the data of both the powder as well as the single crystal information. You get information on what is called the crystallographic information file, which we discussed when we discussed the structure determination in the powder in the single crystal case. So we also have the availability of Cambridge structure database. The literature, of course, we can always go to literature in the end. Earlier days it was the only available source, but now people go to literature only after they don't find anything in these. The way in which now modern day science is done is go to the website. In fact, the way in which anything has to be done is go to the website. You want to know how to make sambar, you go to the website. You don't do it the way we used to do it earlier days. So we first go to the website, get all the ingredients and follow the protocol. So website is become a part and parcel of our life. So we go to the websites, get whatever information we want. So websites therefore have the information you want for all crystallographic data as well. Then of course the databases, these are storage places where you store all the data which is available. It is like your brain, you store the data. So what you learnt in class 3, in general you should be able to recollect when you are reminded of it. But when you don't have to be reminded of what movie you saw when you were a 10-year-old, the moment you are activated you will remember it. So it depends upon what kind of databases we can access, but databases are indeed necessary to get to this. And the last resort happens to be literature. I still remember when we were doing our PhD studies way back in the 70s, none of the top 2 were available, and so we had to go only to literature. I still remember going to the library and climbing up the stacks and removing the dust off the old books and then take it out, the old journals, and see whether the relevant literature is available there or not. It was quite a painstaking methodology which we used to use. So normally when we go to the library, we will be coming out very, very tired and hungry, because we will be climbing up the ladder to access the books which are stored way up there, and then taking it out and opening it, closing it, with removing all the dust, again go up, come down, and each access point will be at different parts of the library, and it depends on the size of the library you are accessing. It would be quite a painstaking exercise. Anyhow, so we can use the PDF to search ICSD listings and follow the references. So ICSD also helps you to, ICSD and also ICDD both, they help to follow the references because they give a list of references. This will help you in looking for isostructural materials, similar structures, isomorphous, isostructural, those materials can be accessed. So this is the access point which we have, and therefore powder diffraction is not just a standalone recording of the PXRD. It now has a lot of information that is hidden in it which we can isolate and identify. So there is the main important thing which comes up in a pharmaceutical industry is the phase identification, the so-called search and match. So there are packages that are available associated with the machines which you use. So the diffractometers which you use, if you use TOE and C, you have a automatic search on peak list or manual matching with raw data or the peak list. If you use Bruker, you have this package called diffract-EVA, which gives you access to automatic search on the background subtracted raw data, automatic search of peak list, and so on. The most recently developed package, which is the HiScore Plus by Panalytical, allows for automatic search of raw data, background subtracted automatically, and also it allows for the search of the peak list. So all these instruments now come with the facility that you don't have to worry too much. You just ask the machine or the computer which is connected to this diffractometers to do the phase identification. It gets automatically done. It not only searches for the required phase, it also matches the phase with the databases. And so we now get a very clear idea of whether we have made a new compound or not. Now here is a situation where we now jump onto the determination of the structure. See, the number of peaks that are produced in a diffraction experiment, whether it is a powder diffraction experiment or a single crystal experiment, are limited to the number of access points we have on the limiting sphere, the reciprocal lattice information. So that means that all the reflections that we can collect on a single crystal should also be possibly collected in a powder. Depends upon what range of 2 theta we are covering. And so if you have a pattern like this, this particular pattern you see is, if you expand the region from 39, I hope you are able to see it, 39 to 45, if you expand that region of the powder diffraction pattern, you will see not very comfortably shaped peaks, but a real distribution of peaks in this region. What one can do is, once you have indexed the pattern, you know the crystal system. It is not generally possible in a straightforward way to determine also the space group, unless of course you do a search match and find out the corresponding crystal system in the database. Otherwise you only have the crystal system. Now once you have the crystal system identified, ABC, alpha, beta, gamma identified for the given compound, then you can calculate how many HKL values are possible and where they can appear in 2 theta. Use the Bragg's equation. So when you do that, you will mark the ones which are marked as horizontal line, the vertical lines here are the ones which actually tell you what are all the peaks that can form. If you look at a region like this, you see that there is a severe overlap of 1 or 2 peaks. It could be 2 peaks, 4 peaks, 6 peaks and so on. This is the problem in analyzing the X-ray powder pattern. X-ray powder pattern is, as we see, it is a one-dimensional profile which is extending over the 2 theta range. And therefore, the individual reflections now may appear under 1 peak, may appear under several individual peaks, may appear under 1 peak. So this is the peak overlap problem. Unless we solve this peak overlap problem, we cannot get the intensities of individual HKL planes. So to do that, there is a procedure called the pattern decomposition. So this is an illustration of how one can do this. I am not going into the detail of how it is done because of lack of time. I think we are almost coming to the last couple of hours of the entire length of the course. So we cannot just spend time on that, but essentially I will tell you how the breakup is done. The breakup is done by actually trying to develop the shape of the profile. So we do what is known as a profile analysis. So the shape of the profile now will be able to be fitted under this particular curve. So this is essentially a curve which is going from 39 to 45, and under that each and every position of HKL is associated with a peak. The shape of the peak, how we assign, I will tell you in a minute, where that is referred to as the profile refinement protocol. So we therefore now what we do is we distribute the peak positions. For example, under this position which you have here, let's take an example, this one particular this peak, for example, at 42, it is a unique peak. There is only one peak. So we can now see that the peak can be fitted with a function which goes under it. The width of the peak and the shape function associated with the peak can be generated mathematically, and how we do that we will discuss in a minute. So we therefore see when there is a severe overlap, there are large number of peaks. For example, in this region, if you consider, there is a peak here 1, there is another peak 2, another peak 3, another peak 4. So all these 4 peaks together will give rise to this profile which you have got in your recorded pattern. So the recorded pattern, why it was looking so funny is because it is made up of 4 reflections. So once we identify those 4 reflections, we can attach individual intensities to that and adjust the intensities in such a way that we mimic the observed pattern. So, we have the calculated intensities, the shape of the profile is evaluated, then you mimic the shape of this. Once you mimic the shape of this, you know now you have fitted the profile, and this process is known as profile fitting, and we can refine this profile with respect to various parameters which are used to describe this function, profile function, and therefore we can do a profile refinement. And when a good refinement occurs, we know that whatever cell dimensions we determine for the structure is very, very accurate. So, it is not enough just to index the pattern and say, okay, this is our compound. You have to also do a profile refinement to verify the indexed pattern and then get the information on individual peaks. See, so far we have not brought the idea of structure. We are not telling where the atoms are and how the atoms are located. We are just trying to fit the profile, and therefore this process is known as profile fitting, which will give an evaluation of the geometry of the situation. If we want to put in the intensity information, that is a different story, which we will see, and that is the one which takes us to the Rietveld refinement protocol. So, let us go further, and we see here the types of profile functions we can fit. You see, we have to get a function which is looking like this, right. So, we have to get a function which will look like that. Let us take this function, this is the profile. So, associated with this reflection. So, in order to get that profile function, we need to have several parameters, and those parameters are supplied mathematically by these following functions. One can use a Gaussian function if one is collecting neutron data. The peaks coming out from a neutron diffraction will always be Gaussian in shape. The reason is obvious, because the diffraction is not from the electron density around, but it is from the nucleus. And therefore, the size of the nucleus is about 10 to the power of 12 centimeters, minus 12 centimeters, and the size of the atom size is about 10 to the minus 8 centimeters. So, it is 4 orders of magnitude smaller, and the incoming radiation is X-ray, and the incoming radiation is also 1 angstrom, and therefore, the shape of the profile is generally a Gaussian. In other words, the atom positions are now very accurately available through the location of the nucleus, and therefore, they all become individually delta functions. So, the Fourier transform of the delta function will be a Gaussian or vice versa. So, we therefore have Gaussian functions very easily fitting neutron data. So, it is recommended that when we have accessibility to a neutron source, powder diffraction data of a neutron is very, very useful. In fact, a powder diffraction data can also help us in finding, once we solve the structure, we can also find the hydrogen atom positions. The only problem is that the neutrons are very, even though they are moderated from a nuclear reactor, they are very, very strong, and therefore, the amount of the powder that is required is quite a large amount. We need gram quantities of the material to do neutron diffraction by powder, whereas you need only a few milligrams, sometimes even a 5 to 10 milligrams, you can get a very good X-ray diffraction data. So, this is the limiting. You see, the two techniques go hand in hand. The technique of neutron diffraction by itself is not a standalone, even though one could say that one can make it a standalone technique, depending on the particular compound which is designed for neutron diffraction. Otherwise, it just goes as a hand in glove technique associated with X-ray. So, X-ray technique is the paramount. It is the first one, which is supreme. And the only issue about X-rays, as we know, is the falling off of the atomic scattering factor with sin theta by lambda, which does not happen with neutrons. So, even though in the syllabus I mentioned we will discuss neutron diffraction, it looks like that we are running short of time. So, whenever possible, I will bring in the advantages and disadvantages of using neutron, and at the same time mention how superior the data from a neutron would be for determining the hydrogen position, because there is no variation of sin theta by lambda fall off of these scattering factors. There is what is known as a scattering length, which is characteristic of the given element, and this value can be both plus and minus, we can normalize it to 1. So, it will be either plus 1 or minus 1, and the range of these values can be occupied by various elements, but these elements now will not show any change with respect to sin theta by lambda. So, it remains the same value throughout the range of the data collection. The other possible fits which are given, we have given 4 of them. It depends on the instrument on which you are collecting the powder data. So if you are using Laurentian data, Laurentian function, you use these parameters. I am not going to tell you what are these parameters, except to tell you that if you take this as the initial position of theta and this is the final position of theta, the difference between these is sort of minimized with respect to these functions. The C1 and C2 constants will adjust the functional parameters. So we have a Laurentian type, mod 1 Laurentian, mod 2 Laurentian, and very often we use this so called pseudo void function. I am not explaining individual values associated. We have used, for example, here H associated with this, and we have used G associated with it. These are all functions which are readily available. So these functions are already available in all the instruments. So it's an instrument the instrument determines the profile function which we normally adopt. So for a routine powder diffractogram where we get from the machines like Panalytical or Bruker, we normally use a pseudo void function for the profile fit. Just remember that. I don't think it is very particularly important.